part 2. This just follows from Marcel de Joux just 1 hour ago. And in this talk, I will mainly focus on the bicommutant theorems. This is a joint work with Marcel de Joux and Bin Dirac. Okay, let's begin with the motivation. Okay, so this is the classical from the human bicommutant theorems. It suggests that if A is a C star subalgebra of B of A should contain the identity operator, then the double commutant of A equal to the strong operator topology of closure of A. And also this topology can be replaced by the weak operator topology. It doesn't matter. It's a lecture question that do we have such a result in Baraha spaces? The answer is no. Even for the commutative unit subalgebra A of B of X, and here X we can choose to be separable with Lex for Baraha space, it may still happen that the strong operator topology closure of A will just be a proper subset of its bicommutant. So this is a paper contains this example, but this is not in English. This paper. Okay. Let's also see another bicommutant result. This is by De Pacta and Rick. And this theorem suggests that for a Mahomet space, and this A to be a unit subalgebra of L infinity, then we have the bicommutant of A just equal to the weak star topology closure of A. I shall explain a bit of this. Maham here means that the associated method algebra is a complete Boolean algebra, and the mu here is just a semi-finite. Okay, the semi-finite means that for a method subset A with its method strictly positive, then we have a method subset A0, which is also a subset of A, such that this method of this A0 is just strictly positive and finite. Okay, we say here that this A is a unit subalgebra of L infinity because we can always see L infinity as a subset of B of LP. This can be done because for every function f, there is a corresponding multiplication operator G act on LP. And then the weak star topology here just means the weak star topology on L infinity. Okay. Okay, let's just explain some notation. And in my talk, this E will always be denoted as that can't complete vector or Baraha lattice. And L of E is the linear operator on E, and LOB of E is the word bounded operator, and LOC of E is what continuous operator. And here B of E is the non-bounded operator on E, and E here is a Baraha lattice. If we let A be a subset of L of E, then we can just give the notation of commutant and bicommutant of A in LOB of E. We will use AOB prime to denote the commutant of this A in LOB of E. It's just a collection of what bounded operates T such that TS equal to ST for any S in A. Okay, this is the bicommutant of A. It's just the commutant of its commutant in LOB of E. So in the same way, we can just use AOC prime and AOC prime to denote the commutant and the bicommutant of A in the word continuous operator space. And if we take E to be a Baraha lattice, then for any subset A of B of E, then A prime and A prime is just as the usual meanings of the commutant or bicommutant. So what do we want for our bicommutant theorems? We want to focus on vector lattice. So we need to first find a situable vector lattice E, and here we let A to be a situable subalgebra of LOC of E. And here, if we think about E to be a lattice, we can think about A to be a subalgebra of B of E. This is also possible. And we want to get such a bicommutant result, a double commutant equal to the topology clause of some topology. So what we need to do is that we first need to figure out what's the tau here. We need to find a tau. Then we also need to find a situable subalgebra, because certainly not all subalgebra of LOC of E can behave so good. So we need some pushings on this algebra. At last, I will just show some result what we have now. So I will first talk about the Hausdorff uo-Lebesgue topology. This has already been introduced and talked in the previous talk by Marcel Dejoux. But still, I will just go through its definition and some properties. An uo-Lebesgue topology here is locally solid topology tau, such that what convergence can imply tau convergence. And uo-Lebesgue topology is a locally solid topology that the unbounded order convergence can imply the tau convergence. So this is the definition of unbounded order convergence. It's just x alpha minus x and which any positive y it can order convergence to 0 for any y. Okay, it's important to mention that vector lattice admits at most one Hausdorff uo-Lebesgue topology. Not all vector lattice can admit a Hausdorff uo-Lebesgue topology. It's like a continuous function space. It doesn't admit any Hausdorff uo-Lebesgue topology, but still we really have a large class of vector lattices admit Hausdorff uo-Lebesgue topologies. So first, we can think about the vector lattices that have separating order continuous duals. For such vector lattice, we always have this tau hat topology. The tau hat topology is just the Hausdorff uo-Lebesgue topology. I will just use tau hat to denote this topology. It's more easy for pronunciation. So let's say the LP space for any P, and the mu is semi-finite. And this tau hat topology is just the topology of convergence in measure. And also for atomic vector lattice, for such a vector lattice, it of course have separating order continuous duals. And the tau hat topology is precisely the topology of coordinate convergence. And another important example is the order continuous black lattices. So what continuous black lattices also admit Hausdorff uo-Lebesgue topologies. We also have an example that it's a multiple function space. So what this space doesn't have separating order continuous dual, but it still admits a Hausdorff uo-Lebesgue topology tau hat. And this topology is just a topology of convergence in measure. So okay, so now we have a topology on E. So we need to construct a strong topology respect to this tau hat on the bounded Walker space of E. So we can define phi x in this way. This is just a map from the Walker space to E. So we can let S tau hat to be the coherence topology on LOB of E, and such that all phi x are continuous. In this case, we need to assume that E is supplied with the tau hat topology. So we will just call this topology the strong topology that corresponds to tau hat. It has an important property that T alpha S tau hat converges to T if and only if T alpha x topological convergence to X for any X in E. Now we give a remark here. So this S topological topology, this strong topology on LOB of E is a topology we are looking for, and we will use this topology for our bicommutant theorems. Okay, so another remark is that the notations like strong word convergence and strong unbounded word convergence on LOB of E can also be introduced, and they also have application in bicommutant theorems. But as a matter of time, I will not give such bicommutant theorems. I will just focus on the topological one. So I will just discuss this strong topology corresponds to this top hat. Okay. So the second, we need to give some assumptions on the subalgebras A of LOB of E. So we need to introduce some properties on the vector lattice. So we first see an important property in Hilbert space. A C star subalgebra A of B of H has the property that if M is an A invariant closed subspace, then M is also A reducing. That means that its disjoint complements is also A invariant. And this property plays a very important role in the proof of the von Neumann bicommutant theorems. So it's very natural for us to try to introduce this property in vector lattices. For that kind of combinator, this property, for every band B of E, it's a projection band, so we can element. Oh, can you hear me?
Yes, there was a dropout for a couple of seconds, but you're fine.
Every band B of E, we can just write E as the direct sum of B and its joint complements. And also for every element X in E, we can just write X as in this way, and this decomposition for L of E, we say that this A has the star property if band B of E is A invariant, then it's also A reducing. So this property just behaves very like the property in the Hilbert space, the C star subalgebra A. Okay, let's give some examples about the subset that have star property. So first, we can think about a subset of isomorphisms on E. It has the star property. This is because for every isomorphisms, it leaves one of the bands of E invariant. so it's obvious that it just T is reducing by one band of E, and of course it has the star property. And also, if we take a conditional expectation operator on P on LP space, then this conditional expectation operator also has the star property, and its reducing bands of P are precisely the band generated by the characterization functions on A, and these A are just a subset of this sigma 0, which is sigma subalgebra of sigma. This is also an example. It's already mentioned in the previous talk by Marcel. And this is a subset of the automorphisms if this A is closed undertaking the inverse. then this A also has a star property. Now it's an easy fact here. If we have subset A has the star property, then we can think about an algebra that is generated by this A and all the isomorphisms on E, and then this A also has the star property. This algebra A. Okay, now we can come to our main course. This is the bicommutant results in vector lattices. We have 4 here. First, the first one is the case when E admits a Hausdorff uo-Lebesgue topology. Yes, and E is Dedekind complete, of course, and it admits this topology tau hat. And for the subalgebra A, we need this algebra to have the star property, and also all the isomorphisms on E are contained in this subalgebra. Then we have the bicommutant of this algebra A in what bounded operator space on E is precisely the strong topology of tau hat and take the clothes of A. This topology is the strong topology we introduced before. Okay, so this is also true for this is also true for the what continuous operator space on E. The second one is about the what continuous Banach lattice. If here we take E to be what continuous Banach lattice, and we can suppose A to be a subalgebra of LOB of E, because in this case E is what continuous Banach lattice. So the what bounded operator are also what continuous. So now we also have this equation. Is double commutant equals to the strong operator topology clothes of A. So I need to mention that in this case, the strong operator topology is different from this strong topology corresponds to this tau hat. This is two different topology. So okay, so I will then give an example to show that in the first result, this condition that A is a subalgebra of LOC of E cannot be renexed to the condition that A is a subalgebra of LOB of E. So we really need this A to be contained in the what continuous operator space. And also in the second theorem, we need the assumption that E has the what continuous norm. And this is the example. This works for. This is the counterexample. So we can take E to be in the small L infinity, and we can define this FC to be a positive linear function on C in this way, and then we can extend this function FC to L infinity, because C is just a majorizing sublattice of L infinity, so it's possible for us to extend this F to FC. And then we have this T to be the tensor product of F and E1. So we also define some Tij here. These Tij are operators that are also what continuous operators on L infinity. So we can think about the algebra A that is generated by T and all such Tij and all the isomorphisms on E in LOB of E. Then we have that this A has a star property, and of course it contains one isomorphisms on E. But it's true that the double commutant is not the double commutant is just equal to the whole space, but the strong topology clothes is just a proper subset of its double commutant. So this is the counterexample. So still we have the last two bicommutant theorems. This is an atomic vector lattice. We can let it to be atomic delicate component, and also we need an algebra A to be a unitary algebra of LOB of E with a star property. And then this A is also a bundle of LOB of E, because in this case E is delicate component, so LOB of E must be a delicate component vector lattice too. So okay, so we also have this bicommutant equation here. The last one is the case when is atomic Balk lattice and also has the water continuous norm. In this case, then the result is very nice. So this algebra A just contained in B of E, not LOC of E. This is bigger. And this A has a star property, and also we need the osmosis on E are contained in A. Then we have the double commutant of A. This double commutant is just as the usual meanings of double commutant. It's just in B of E, and it's precisely in a strong operator topology of closure of A. Okay, I think that's all of my talk. Thanks.
Thank you. Are there questions for the speaker? I'm sure there are. Let's give it a few minutes. I'm sure you couldn't have answered everyone's questions. Marcel, do you have any questions for the speaker?
Maybe you could just give us a hint of what type of non-topological double bicommutants you have. Maybe it's hard, you cannot write maybe, but not online, but is it possible to describe in words what topologies will occur or convergence structures will occur and what it looks like?
First, sorry, Marcel, I didn't follow you. You meaning?
No, you have covered only a small portion of your work, which is on topological bicommutant theorems. Can you maybe just indicate what results you have on non-topological bicommutant theorems?
Yes, it's possible, but in that case, we need to assume this. So because all the bicommutant theorems here, we will assume that the osmosis is a subset of A. You see. But if we can also let the subalgebra A to be a subset of the osmosis. So when we think about the converse, we just think about A to be a subset of osmosis on E. So then the convergence structures like water convergence and unbounded water convergence will be very useful to describe the double commutant of A.
But that is when you work in the orthomorphisms, right?
Yes, yes.
Okay, yeah. So here you're still more general. I see. Yeah, thank you. Yeah.
Thank you. Yusuf Azuzi, you have a question.
This work is motivated by the bicommutant theorems, I think.
Yes.
So, is there another famous result or other result which can be considered in the next step?
So you mean that is there any connection with my result with the classical one?
I don't know, but
maybe if Jan allows me, I can speculate on that.
Yeah.
My original mathematical background is in representation theory of Lie groups, and then I have always liked abstract theory of unitary group representations. And you can always disintegrate a unitary group representation into irreducibles. And one of the major steps in that is that you take a C-star algebra and realizes operators on Hilbert space, and you take a maximal abelian subalgebra of its commutant, and then you first disintegrate the representation, the space with respect to that action, and then you have it for the C-star algebra, and then also for the groups. And I'm personally hunting for such a theorem. And my motivation for this is that I would like very much like to know what the proper analog is for Neumann algebras in vector lattices and in Banach lattices, because these are crucial in representation theory in Hilbert spaces. So if there's a famous result which is to follow, hopefully from this, it will be a disintegration result of group actions on the Banach lattices. And this might be a part of this, but it's not. Well, it's a next step.
Okay.
Thank you.
Thank you.
Are there any further questions for the speaker? Otherwise, we will start the next talk in 4 minutes, and that will be Marwa Masmoudi will